Good morning, dear students. Let us see a session on magnetic materials. Before going into the details of magnetic materials, let us see what is magnetism. A magnet, to say very specifically, an electromagnet is very important for electrical machines because the basic working itself is depending on the electromagnetism. So, what is magnetism? Magnetism is a phenomenon by which material exerts either attractive or a repulsive force on another. How does this magnetic force developed? Basic source of this magnetic force is movement of electrically charged particles. Thus, the magnetic behavior of a material can be traced to the structure of its atoms. It is all the quality of their atoms. So, electrons, if we check in detail, it has a movement which is similar to a planetary motion. The electrons go around the nucleus as how the planets are going around the sun. Correct? And this orbital motion and its own spin cause a separate magnetic moments, which is the one becomes the basic of magnetic behavior of a material. So thus every material can respond to a magnetic field because every material has atoms and the atoms has its own spin, and the electrons in that particular atom has its own spin and it is going around the nucleus. So, however, the manner in which the material responds depends much on its atomic structure. That is, for every material the atomic structure differs, and based on this atomic structure you can say whether this particular material is a strong magnet or a weak magnet. What is the strength of magnetism for that particular material? So how do we calculate this magnetic moment? Because based on the magnetic moment we said that one material will show the magnetism. So magnetic moment is calculated by Bohr magneton, which is given by an equation QH by 4 pi into ME, that is Q is the charge on the electron, H is the Planck's constant, and ME is the mass of the electron, M suffix E. Bohr magneton is the most fundamental magnetic moment. So what do you think, whether all materials are magnet? Because as per our previous argument, every electrons which is having a planetary motion around the nucleus keeping on moving and it has a magnetic moment. So once every electron has or every material has a magnetic moment, then it should definitely act as a magnet. But no, it is not the case. So what is the reason for a material to become magnet and not to become magnet or not have a magnetic property? So generally in materials, two electrons with the same energy level must have opposite spins. Thus their magnetic moments generally cancel each other. That is the property of general materials. The electrons will have spin, both will be spinning, but it will of the same energy level. Right? It will be spinning opposite, so that even the magnetic moments also will be opposite and they will get cancel each other. And the second reason is that orbital moments of electrons also can cancel out each other, thus having a resultant zero net magnetic moment. Some elements such as transitional elements, lanthanides and actinides have a net magnetic moment because of their energy levels have an unpaired electron. There is no same energy level electron. So you call it as an unpaired electron. So such material show the magnetic property. Now what is a magnetic dipole? Magnetic dipole is very similar to an electric dipole. The electric dipole, when we say, it is a positive and a negative terminal, correct? Same way the magnetic dipole is also a north pole and a south pole. Okay, it's analogous to the electric dipole. So in a magnetic field, the force of the field exerts a torque that tends to orient these dipoles along the field or with the field. The magnetic forces, how does this magnetic force generate? It is generally generated by movement of electrons, electrically charged particle. General electrostatic energy will be there. So this movement of electric charged particles is on top of that. It's additional movement. And it is convenient for us to think that the magnetic field will be kind of a distributed field which is represented by imaginary lines. These lines also indicate the direction of force. I can show you a picture of this magnetic lines. Just a second. So you can see this magnetic lines. This is the picture. You can see that the magnetic lines are going from north pole to south pole here, north pole to south pole. These are magnetic lines of force. So once the electrons get the charge, it has a movement and creates the magnetic moments, and then it keep moving. It forms imaginary lines of force. Right. Now we have to understand how this magnetic field can be measured. Okay, it is measured based on a term which is called as magnetic field intensity or magnetic flux density. All these terms will point us to the measurement of magnetic field. So if a magnetic field is generated by passing current I through a coil, which we generally call as an electromagnet, through a coil of length L and number of turns N, then the magnetic field strength H, unit is ampere per meter, is given by H is equal to N into I by L, or HL is equal to N into I. Now what is a magnetic flux density? It is a measure of lines within a medium. It has a unit of Weber per meter square. Okay, so magnetic flux divided by the area, or Weber per meter square, or Tesla, and could also be defined in terms of and in relation to the magnetic field density as B is equal to mu H, where mu is the permeability. It is a specific property of the medium. Alright, and relative permeability, there is one more term which is called as a relative permeability, which is mu R, which is equal to mu by mu 0. Alright, so mu R is a measure of the degree to which the material can be magnetized, where mu 0 is the magnetic permeability of the vacuum. So hence generally we say mu B is equal to mu H. This mu is actually mu naught mu R. Mu naught is the magnetic permeability of vacuum, and mu R is a measure of degree to which and the magnetic permeability of the material whatsoever. That is the material. So now we'll go to types of magnetism. Just a second. I think we were here, types of magnetism. Alright, so let's see this. So a material, I am here, you may understand that types of magnetism. Okay, a material is magnetically characterized based on the way it can be magnetized. Right? This depends on material's magnetic susceptibility, its magnitude and sign. Three basic magnetisms are. What are the different three types of magnetism? Which is a diamagnetism, a paramagnetism, and a ferromagnetism. So there are three types of magnetism, in which diamagnetism, which is a very weak magnetism, only when you apply an external field, then it will have its magnetism. So it's a non-permanent magnetism. Alright, so and the strength of this particular magnetic field is very, very less. Alright, materials such as copper, silver, silicon, and aluminium, these are all belong to all belong to the diamagnetic structure. Paramagnetism is slightly stronger, right, which when an external field is applied, in that case the dipoles align up with the field, resulting in a positive magnetization. However, the dipoles do not interact. Materials which exhibit small positive magnetic susceptibility in the presence of magnetic field are called paramagnetic, and the effect is termed as paramagnetism. Right. So there is only when, again this is also when only when an external field is applied. Okay. In this again we have to say that you need extremely large magnetic fields which are required to align all of this dipoles. Okay, so we don't recommend even paramagnetism also. It is present, the materials which shows paramagnetism are aluminum, calcium, titanium, and some alloys of copper, and the magnetic susceptibility of the material is slightly positive, that is from plus 10 raised to minus 5 to 10 raised to minus 2. Both dia and paramagnetic material, generally we consider them as non-magnetic because they exhibit magnetization only in the presence of an external field. Certain materials possess permanent magnetic moments even in the absence of an external field. Okay, these result of permanent unpaired dipoles form from unfilled energy levels. These dipoles can easily line up with the imposed magnetic field due to the exchange interaction or mutual reinforcement of dipoles. These are called ferromagnetism. Okay, this is the susceptibility range is very much positive. It is about 10 raised to 6. Okay, you can calculate the susceptibility by the following equation, which is C divided by T minus Tc, where C is the material constant, T is the temperature, Tc is the Curie temperature. Ferromagnetics are very strong, alright, and the dipole line up permanently upon application of external field. This ferromagnetism you can again classify into two different types. One is an antiferromagnetism, another is a ferrimagnetism. Alright. Now this antiferromagnetism, as you can see, there are so many metals which show this antiferromagnetism, which is when the dipoles line up in opposite directions, it will show zero magnetization. So it has a very strong magnetization, but since it is opposite direction, the net effect becomes zero. So the materials which show antiferromagnetisms are manganese, chromium, manganese oxide, nickel oxide, cobalt oxide, manganese chloride, dichloride. All this shows antiferromagnetism. Ferrimagnetism is the materials which exhibit a net magnetization. So iron oxides, nickel iron oxide, most of the iron oxide and all these things which is shown, all the materials show a net magnetization which you call as a ferrimagnetism. Alright, so this table shows a summary of what is a magnetic susceptibility and what type of magnets are magnets, paramagnets, ferro, antiferro and ferrimagnets. Right. So generally we use ferromagnetic materials for our machine parts. Okay. Now what are the magnetic domains? So I think this curve will give you a magnetic saturation curve. This is right, as the magnetic field intensity is increasing, the magnetization increases, and at one particular point it reaches the saturation. This we call as a magnetic saturation curve. And there is a property called as magnetic hysteresis. Magnetic hysteresis is that once the magnetic saturation has been reached or achieved, a decrease in the applied field back to zero results in a macroscopically permanent or residual magnetization, which we call as remanence. And it is denoted by Mr. The corresponding induction Br, which is called retentivity or remanent induction of the magnetic material. This effect of retardation by material is what we call as hysteresis. The magnetic field strength which is needed to bring the induced magnetization to zero, which is called as coercivity Hc, which is marked here. You can see Hc. This must be applied anti-parallel to the original field. Right? A further increase in the field in opposite direction results in maximum induction in the opposite direction. The field can once again be reversed and the field magnetization loop can be closed. This loop is known as hysteresis loop or BH plot, or even we can say, like the previous one, it is an MH plot. So here only thing is we try to bring the magnetization back to zero, giving an opposite magnetization. That's why the hysteresis curve developed. Okay. So now we can see the different types: semi-hard magnets, soft magnets and hard magnets. These are the different types of magnets. So semi-hard magnets is the area within the hysteresis loop represent the energy per unit volume of material in cycle. The coercivity of the semi-hard magnets material is a microstructure sensitive property. Okay, and this hard ferrites based on barium, chromium oxide, iron oxides, and all these alloys of cobalt, platinum, tantalum, chromium, iron and platinum, and iron and palladium. All this comes to the category of semi-hard magnets. Soft magnets, which are characterized by low coercive forces, low coercivity and high magnetic permeabilities. So these also, they generally exhibit very small hysteresis losses. And hard magnets, if you observe, are characterized by high remanent inductions and high coercivities. These are also called permanent magnets or hard magnets. So they are cobalt steel, tungsten steel, alnico, and all these things belong to hard magnets. So these are the different classification of magnets and different types of magnetism. In electrical machines, we generally use electromagnets. There are permanent magnet machines also, but general popular and economical machines are made up of mostly electromagnets. So it is very important for us to understand that which type of material need to be selected for the construction of the machine, so that you get a maximum magnetization and a good working flux. So this shows the significance of understanding the magnetic materials and to have a proficiency in selecting the magnetic materials for a better machine construction. Thank you all. If any questions related to this, we may discuss in the class. There will be a questionnaire sent to you. Kindly fill those questionnaire and understand in detail what is different magnetic materials. Thank you.